Manual auscultation is the legacy method in identifying respiratory diseases incorporating X-rays and other types of scans. Those legacy methods rely heavily on the expertise of the medical practitioner. There are a reasonable number of deaths around the world due to chronic respiratory diseases. According to the World Health Organization, more than 45% of WHO state members have less than one physician per 1,000 population, which is deficient. So, there is a clear need for a system to act as a supporting tool for medical practitioners as well as a learning tool for medical students in the process of identifying lung diseases. As a solution to this problem, we developed a mobile application named PulmoSync, leveraging deep learning techniques that support uploading of lung sound audio and detect whether the lung sound is healthy or abnormal more efficiently. As an extension for abnormal conditions, we classified the lung sound into one of 9 different respiratory diseases. Not only the classification but also interpreted the prediction of the classification using explainability techniques. We started with exploring deep learning approaches for audio classification as well as image classification. Then we developed the deep learning pipeline and trained the classification models. After that, we employed explainability techniques to interpret the prediction, and then we developed our mobile application and integrated the deep learning pipeline to deploy it as a supportable tool. So, let's dive into the captivating world of deep learning and witness how it solved a major medical problem using PulmoSync. First, we created our lung sound dataset by combining the ICBHI 2017 respiratory dataset and a dataset collected by another research group. Then we applied normalization and data augmentation techniques like pitch shifting and data splitting to mitigate the data imbalance of the dataset. Then we extracted 3 audio inheritance features: MEL spectrogram, MFCC, and chromogram. Then we stacked these 3 spectrograms to create a 3D representation just like the RGB layers of an image. Then we fed this 3D input to our classification models, which are developed in CNN architecture. Classification is done in 2 phases. First, there is the binary classification model, which detects whether the patient is healthy or abnormal, enabling early exit for healthy lung sounds. If the lung sound is an abnormal one, then it will go to the second classification model, which identifies the disease out of 9 respiratory diseases. The prediction given by the classification model is then interpreted utilizing explainability techniques. Then the whole system is integrated into a mobile application. The binary classification model was able to achieve 96.55% accuracy, while the multi-classification model was able to achieve 91.04% accuracy. Explainability results were calculated using a masked dataset and were able to prove our explainability approach. Let's go to the PulmoSync mobile application. The PulmoSync has the functionality of uploading a lung sound audio. The uploaded audio will send to the Flask backend to do the feature extraction and the classification. Then the results will be sent to the Java native front end. If the lung sound is healthy, the application will show the probability of the patient being healthy, accompanied by a disclaimer advising consultation with a medical practitioner despite the indication of health. If the lung sound is abnormal, PulmoSync will display the 3 top most probable diseases that the patient can have with their probabilities. As an example, the probability that the patient can have pleural effusion is 92.54%. These probability values will be represented graphically using a radar graph. The explainability results will be displayed in the application with the functionality of playing the lung sound audio again if necessary. Finally, a PDF will be generated, encapsulating the classification results. Not only with the classification results, but also we were able to evaluate the mobile application with a System Usability Study, SUS, which provides a fast and accurate way to assess the usability of a system. The SUS survey consists of 10 questionnaires where odd-numbered questions address positive aspects, while even-numbered questions focus on the negative aspects. This study was conducted by using a group of 21 medical students to evaluate their opinions on the functionality of the system and their interest in using it. The proposed system has shown an average SUS score of 73.21%, indicating good usability. These results show the opinions of medical students, and the usability of the system can be further enhanced by having training sessions to assist users in understanding the system's functionalities. We were able to develop a supporting tool for medical practitioners as well as a learning tool for medical students which assists in identifying respiratory diseases. As a novelty, we were able to classify lung sounds into 10 different classes, including healthy classes, in a two-phase approach. We were able to extract and stack 3 types of audio inherent features to capture more features in the audio to gain a better classification performance. And also we were able to interpret the prediction of the classification using explainability techniques. With PulmoSync, you can streamline the process of identifying respiratory diseases and get the results you want within seconds. We hope PulmoSync will open a new gate as a precise and efficient member in the domain of lung sound classification, which will revolutionize the way healthcare professionals diagnose and treat respiratory conditions. Ultimately, we hope that PulmoSync will lead to improved patient outcomes and a healthier society.